Hi there. Glad to see that you found me. I am here to talk to you a little bit about Kepler's laws. That's what we're going to be doing in the class for the next few days. We're going to do a lab on ellipses and then follow that up with how that applies into Kepler's laws. Now, these laws are all about planetary motion. When we talk about planetary motion, we're talking about orbits. This was all developed in the early 1600s, about the same time as Galileo. This is what we would refer to as kind of the renaissance of astronomy. Prior to this time, we were still thinking that the sun was the center and everything went, excuse me, not the sun, but the earth was the center. And Kepler, Galileo were two astronomers that changed the way we thought about how things worked. So his laws, there are three of them. We'll talk about them and then I'll try to give you some examples. His first law says that the orbits of the planets are ellipses with the sun at one focus. So I want to talk about this word ellipses, and we're going to do a lab to hopefully get you to understand how ellipses work. You might have heard this in math class, but ellipses is a type of geometric figure, and it's got some properties. It's related to a circle. It's probably also related to a straight line. His second law says that a line drawn from a planet to the sun sweeps out equal areas in equal intervals of time. And the upshoot of that is right here, that a planet must move more rapidly when it's closer to the sun and more slowly when it's farther away from the sun. We made mention of this a little bit earlier when we were talking about seasons. So that's his second law. And his third law is also known as the law of harmonics. It says that the square of a planet's orbital period, and that would be in years, that's this p value right here, p squared is equal to, or it's proportional to, the cube of its average distance from the sun. And I just love it when things work out mathematically, and we will take a look at this and be able to see how that works for the different planets. Okay? So, let's talk about this one more time. We talk about planets orbiting the sun in a figure called an ellipse. And what you're looking at here, this is an ellipse. And you've got the sun right here. This is in a focus. An ellipse is different from a circle in that it has two center points. We call them focus. The sun is one. This point right here is usually in empty space somewhere. And the planet's going around. This is a very magnified ellipse. The long part of the ellipse right here is called the major axis. The short point of the ellipse is called the minor axis. Okay? When I'm closest to the sun, we say we're in perihelion. When we're farthest from the sun, it's called aphelion. So this is what we're going to be working with on our first lab here starting tomorrow. His second law says that if we pick equal intervals of time as the planet is orbiting around the sun, so as I go around the sun here, each of these letters marks out an equal interval of time. And so what do I notice about this? Well, the interval that I'm traveling from here to here is a lot farther than the interval I'm traveling between these two. And you might ask yourself the question, why is that? And the reason is because as we are farther from the source of gravitation here, my velocity is going to be slower. So I'm going to move slower here because I'm closer to the sun here, I am moving faster. That's the way things work. And that's what his second law talks about. The third law is, again, if I have, looking at p squared and a cubed, this is my period. This is the time it takes for me to go around the sun. And we measure that in years. This is the average of my distance from the sun. Okay? It's my semi-major axis. And that's in something called AUs. That's the distance the planet is from the sun, the average distance the planet is from the sun. If I square this value, cube that value, they are equal to each other. Or if I put p squared and divide it by a cubed, what should I get? What number should I get? If these two are equal to each other, I should get something very similar to 1, or very close to 1. And we'll do that a little bit for you. So, those are Kepler's 3 laws. That's what we're going to be working on in the next 3-4 days. If you've got any questions, I will ask for them in class, and please, please, please share your question with me. Thank you very much.